every highway you have ever traveled on, every tunnel you have ever passed through, every house you have ever lived in, almost all of them share one ingredient. Not timber, not steel, not stone. Concrete, plain, gray, forgettable concrete. Humanity produces so much of it each year that if you stacked it into a single wall, that wall would circle the entire planet more than once. That is not an exaggeration. That is simply the arithmetic. Concrete is the second most used material on the planet. Only water is consumed more than coal, more than copper, more than lumber. And because of that, modern construction has revolved around it for more than 100 years. But here is what almost nobody talks about. Producing concrete pumps an enormous volume of carbon dioxide into the air. The cement sector by itself accounts for nearly 8% of every greenhouse gas humans release each year, more than the entire global aviation industry combined, almost equal to every vehicle on every street on the planet. In 2025, a group of Chinese researchers silently released a study claiming to transform how concrete gets made. Engineers across Germany, Japan, and South Korea began scrambling to catch up. That alone was worth noticing. Concrete has barely evolved in over 100 years. The method of mixing, pouring, and letting it set has remained nearly identical across generations. Every construction code in every nation still assumes concrete behaves exactly as it always has. In this video, you will discover exactly why this issue went unsolved for decades. What a group of scientists spread across 3 Chinese institutions uncovered that changed the game. An entirely different Chinese innovation that is questioning whether structures even require this much concrete in the first place. And why engineers in Germany, Japan, South Korea, and the United Kingdom are now racing to patent ideas built on Chinese findings published only months ago. If you want to know what's unfolding globally before it becomes mainstream news, smash that like button and subscribe now. It truly helps this channel grow. Let's dive in. Concrete is honestly one of the smartest materials ever created. Affordable enough that even poor nations can use it at massive scale. Tough enough to support entire skyscrapers. It can take the shape of whatever a designer imagines. It sets on its own without any extra processing. It does not corrode like metal, does not decay like timber, does not crack like glass. For nearly all of human existence, nothing else came close to delivering all of that together. That is precisely why it is so difficult to replace. The issue is rooted deep within the chemistry itself and cannot simply be engineered out. To produce cement, the binding agent inside concrete limestone must be heated past 1,200 degrees Celsius. At that point, the stone decomposes and emits carbon dioxide as a direct chemical result. This has nothing to do with running on dirty power. Even if every furnace on the planet ran on completely clean energy, you would still get enormous carbon output purely from the rock itself. The emissions are written into the formula. Quite literally. Now scale that up to match global cement demand. China by itself, between 2011 and 2013, used more cement than America used throughout the whole 20th century. Not across a generation. Not across a decade. In just 2 years. For decades, scientists attempted to slowly fix the issue. Some swapped portions of cement for industrial leftovers. Others engineered alternative chemical compounds. A handful tested carbon capture systems at factories. These attempts produced minor improvements. None of them shifted the underlying economics enough to scale worldwide. The basic method of mixing, pouring, and waiting for it to set remained almost untouched. The question nobody had truly investigated was remarkably straightforward. What if the issue was not the ingredients going into the concrete, but what happens to it right after it leaves the mixer? The hidden story pressure changes everything. Wet concrete is not a solid object. The moment it gets mixed, It becomes a heavy liquid mixture loaded with water, trapped pockets of air, and scattered grains of cement and rock. Typically, you pour it into a frame and let it sit. Gravity contributes a little. Vibrating equipment assists somewhat. Across time, the grains settle, the moisture gradually escapes, and the mixture sets firm. This method has stayed basically unchanged across decades. The scientists working out of Tongji University, the China Building Materials Academy, and Shanghai Jiaotong University chose a different approach entirely. Rather than relying on gravity and waiting, they introduced mechanical force onto the fresh mixture while it remained wet and pliable. Somewhere between 5 and 15 megapascals of pressure. Similar to the force generated inside an industrial-grade hydraulic press. Compress the material from every side. Picture the contrast between a loose mound of sand and a tightly packed slab of rock. The grains were pushed together so firmly that surplus water and trapped air were forced out completely. The mixture turned noticeably denser almost instantly. The overall porosity of the material, the share of volume occupied by microscopic gaps and holes, fell by close to 45% versus standard mixing. These microscopic gaps are where nearly every structural issue originates. Fractures begin at gaps. Moisture infiltrates through gaps. Salt and ocean chemicals travel through gaps to reach the metal reinforcement within, triggering corrosion that can eat away a structure from within. Shrink the gaps, and you resolve most of concrete's lasting vulnerabilities in a single step. But the biggest shift occurred at a junction most people are unaware of. Within every piece of concrete sits a microscopic zone where the cement coating meets each piece of rock. In ordinary concrete, this junction is the weakest point in the entire structure. Under compression, casting this junction tightened, noticeably showing as much as 35% fewer gaps compared to ordinary concrete. The fragile point in the chain became substantially tougher. Compressive strength climbed by more than 80% in the strongest pressure trials. And here's the detail that grabs every engineer's attention. The researchers accomplished all this without introducing anything new into the mixture. No costly additives, no unusual materials, no altered formula. The exact same ingredients treated differently created a noticeably superior result. The steel challenger and the building that went up in 30 hours while the concrete story was playing out in research journals, a completely different technology was developing in parallel. It was rethinking not just how concrete is made, but whether some buildings need much of it at all. It is called BCore. Developed by Broad Group, a Chinese company with a history of doing things in construction that most people assume are impossible. The core panels look deceptively simple from the outside. Two thin steel skins held apart by a precise grid of hollow steel tubes arranged in a geometric lattice. The whole structure looks a little like the inside of a waffle iron, but engineered to a tolerance measured in fractions of a millimeter. The design borrows from aerospace engineering. The same basic logic that allows an aircraft fuselage to be both incredibly thin and incredibly strong. The steel skins handle tension and compression. The pipe lattice handles bending and twisting. Together, they create a panel that weighs less than a tenth of a comparable reinforced concrete slab while carrying similar structural loads. In 2025, a 10-story building in Chengdu was assembled using BCore modules in under 30 hours. The workers were not rushing. The system is simply designed for speed, the same way flat-pack furniture is designed to go together without special tools. What makes this more than a novelty is the seismic performance. Traditional concrete structures are heavy, and heavy things are hard to move. When the ground shakes, all of that mass creates enormous forces the building has to absorb. Lighter structures built with BCore panels absorb and redirect those forces differently. Seismic testing showed the panels handled shock and vibration with a resilience that conventional concrete frames struggled to match. In regions where earthquakes are a real concern, which covers a significant portion of the world's most densely populated areas, that is not a minor detail. It is a fundamental safety advantage. BCore and compression cast concrete are solving different problems, but they are pointing in the same direction. One makes the concrete that does get used far better and far greener. The other reduces how much concrete a building needs in the first place. When you put them together, the combined impact on cost, speed, weight, and emissions is far larger than either technology delivers on its own. What America is actually doing, and why the world is racing to copy China news and construction science, does not usually travel fast. Building codes take years to change. Large companies move cautiously because the consequences of getting a structural material wrong are measured in human lives. So when international interest in compression cast concrete and BCore started accelerating within months of the 2025 publication, it was a sign that the industry recognized something genuinely different was happening. 34 international patent families now cite the original Chinese research. Filings from Germany, Japan, South Korea, and the United Kingdom. These are not reference citations in an academic paper. These are companies and research consortiums putting legal and financial resources behind the technology. In 2026, China exported 12.44 million metric tons of carbon-cured concrete additives to the United States, the United Kingdom, and Southeast Asia. A tenfold increase compared to just 2 years earlier. LafargeHolcim, one of the largest cement producers on the planet, signed a 5-year licensing deal with Beijing Cement Group. Germany ran compression cast deck trials on a real highway project near Berlin. Japan's Obayashi Corporation launched a joint research program with Beijing University of Civil Engineering. South Korea's Hyundai Engineering announced plans to build a domestic BCore panel factory. What is driving this is not idealism, it is math. In regions where carbon emissions are taxed or capped, a 40% reduction in cement use translates directly into lower regulatory costs. Cutting the price of the most expensive ingredient in your product while simultaneously making that product stronger is not a trend. It is a competitive advantage that no serious company can afford to ignore. On the Pingjiang River, 150 meters of bridge deck built with compression cast concrete were monitored continuously for 12 months. The in-place compressive strength averaged 61 megapascals, exactly matching the lab predictions. 0 visible cracks. Stable moisture readings throughout. The claim now has receipts. How big could this actually get? And the honest challenges ahead here is the honest picture. The numbers that researchers attach to the potential scale of this are almost hard to believe until you remember how much concrete the world pours. Life cycle models suggest that switching just 30% of new structural concrete worldwide to the compression casting process could cut annual carbon dioxide emissions by around 850 million tons. To put that in perspective, that is more than the entire country of Germany produces in a year from every power plant, every factory, every car, and every farm combined. One process changed, applied to less than a third of global concrete output, delivering that kind of climate result. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets difficult. Building codes in most countries are updated on timescales measured in years, sometimes decades. They move slowly by design, because the cost of a structural failure is not just financial. Every country that wants to adopt this at scale needs its own independent testing, its own regulatory approval, and its own trained workforce. China can share the blueprints, but the rest of the world has to do the work of adapting them locally. There is also the question of infrastructure. Compression casting requires equipment that most concrete plants do not currently have. For large construction companies and wealthy countries, that investment may pay off quickly. For smaller contractors and developing economies, the barrier may be much higher. None of these challenges change the underlying reality of what the science shows. They simply define the gap between what is technically possible and what will actually happen at scale. What is clear is that for the first time in a very long time, the fundamental process of making and using concrete is actually changing, not just at the margins, not just in a laboratory, in real structures that real people are using right now. And given that concrete is the second most consumed substance on Earth, with only water ahead of it, changes to how it is made do not stay small for long. If this video changed how you think about something you walk on and live inside every single day, hit the like button and subscribe so you never miss what we cover next. Turn on notifications because these stories move fast and you do not want to be the last to know. Now here is the question I want you to think about and answer in the comments. If a process changes this significance, has been hiding in plain sight for decades, what other obvious breakthroughs do you think engineers are sitting on right now? Drop your answer below. I read every single comment, and I genuinely want to know what you think.